Welcome to this explainer. Today, we're setting the stage for what is, honestly, the ultimate cosmic mystery. We're going way, way back to the very beginning of literally everything, right to the absolute edge of the known universe. You know, it's a pursuit that has fascinated scientists and philosophers for decades. Though, to be fair, if you ask a theoretical physicist what came before the Big Bang, they might just roll their eyes at you. It's notoriously one of the most frustrating questions in all of cosmology. But hey, we aren't going to let that stop us, right? We're diving headfirst into the math, the models, and the absolute madness of the pre-universe.
Part 1. The accepted beginning. Let's establish our cosmic baseline.
Okay, let's dive into this. For nearly a century, science has operated on this foundational assumption about exactly how and when our universe actually started. It's the baseline for all of modern cosmology. So let's mentally strip away everything we know today and journey backwards. We can skip right past the dawn of human civilization 10,000 years ago, past the formation of the Earth 4.5 billion years ago, and even breeze right past the ignition of the very first galaxies 13 billion years ago. We know the universe had already been evolving long before those milestones, but when we trace that evolution all the way back, we eventually hit a definitive hard wall at 13.8 billion years ago. This is our limit. It's the absolute edge of the observable universe.
13,800,000,000 years. That is a massive number. And it's our widely accepted beginning, the precise moment when space, time, matter, and energy all rapidly expanded. But to really get a feel for this, we have to look past the standard textbook definition of the Big Bang. We are talking about an environment so unimaginably dense and hot that the fundamental forces of nature were literally squished together into a single force. We trace it back to a fraction of a second after the initial singularity, a moment where our current laws of physics just completely break down. According to our standard models, everything we know, everything we can observe, and everything we are just expanded outward from that incomprehensibly dense microscopic speck. Crazy, right?
Part 2. The Cosmic Wall. Confronting an impossible paradox.
Reaching that 13.8 billion year mark doesn't just give us a neat origin story, it forces us to confront a really severe dilemma. Seriously, what happened before the Big Bang? Was there an earlier universe? Did time even exist? Or is the word before just a completely meaningless concept? Stephen Hawking famously said that asking what came before the Big Bang is like asking what lies north of the North Pole. If time itself was forged in the fires of that initial singularity, then before simply doesn't mathematically compute. But, theoretical physics doesn't exactly like dead ends. Just because our conventional concept of time might have a starting point, well, that doesn't necessarily mean the cosmos itself sprang from absolute nothingness.
Part 3. 4 pre-Big Bang theories. Let's look at the 4 leading suspects.
Now, what's really interesting about this slide is how our first suspect, quantum fluctuation, scales the microscopic all the way up to the macroscopic. In quantum mechanics, we know from Heisenberg's uncertainty principle that empty space is never truly empty. A vacuum is actually this bubbling soup of virtual particles just popping in and out of existence. Some physicists theorize that our entire universe emerged from just such a random, microscopic energetic jitter. Imagine a vast, endless state of potential. A tiny quantum fluctuation happens, but instead of collapsing back into nothingness, it triggers a period of rapid, exponential expansion. We call that cosmic inflation. So in this model, our vast universe is essentially a subatomic glitch that somehow managed to inflate to a macroscopic scale. Then we have our second theory, the cyclic universe. In this scenario, our Big Bang wasn't the definitive beginning of everything, but rather a cosmic reboot. Think of it as a big bounce. Physicist Roger Penrose championed a mathematically rigorous version of this. The idea is that over trillions and trillions of years, a universe expands, cools, and decays until all matter is swallowed by black holes, which then eventually evaporate. The resulting ultra-expanded, empty, freezing universe mathematically loses its sense of scale and time, effectively hitting the reset button into the hyperdense, hot state of a new Big Bang. If this framework is actually true, our universe is merely an aeon, just one single iteration in an infinite sequence of collapsing and blooming cosmic chapters. It's an endless loop.
Okay, if that wasn't mind-bending enough for you, our third theory requires us to step completely outside our standard 4 dimensions. This is the brane collision theory, born directly out of string theory and M theory. M theory posits that our universe exists within an 11-dimensional space, and within this bulk space, there are massive, multi-dimensional membranes, or branes for short. This theory suggests our observable universe is situated on one of these branes, just floating through a higher dimensional void. Occasionally, 2 of these titanic branes drift together and violently smash into each other.
The sheer kinetic energy of that multidimensional collision transfers into the brains, creating a massive influx of heat and energy that we perceive from the inside as a Big Bang.
And that brings us to our final suspect, eternal inflation and the multiverse hypothesis. In the Standard Model, the early universe expanded exponentially for a tiny fraction of a second. But eternal inflation argues that this rapid expansion never actually stops everywhere. Instead, space is inflating infinitely, driven by this high-energy vacuum. However, in localized pockets, the inflation sort of slows down and energy gets converted into matter and radiation. Our universe is one of those pockets, just a stabilized bubble floating in a boiling sea of eternal inflation. Out there in the multiverse, bubbling way beyond our cosmic horizon, countless other universe bubbles are constantly being born. And the truly wild part here? Each bubble might freeze out with its own completely unique laws of physics. No way to know for sure.
Let's move to and see how this builds. Part 4. Searching for hidden clues. The hunt for scientific evidence.
We've looked at the theoretical math, but to shift from high-level physics to proven science, we need hard evidence. And this brilliantly illustrates the absolute greatest challenge scientists face right now. On one side, we have the cosmic wall, because the early universe was this super opaque plasma. Literally no light can travel to us from before the 380,000-year mark after the Big Bang. It's a hard barrier. But on the other side, we have our absolute best hope for peering into the deep past, the cosmic microwave background, or CMB. This is literally the oldest radiation in the universe. Cosmologists are rigorously mapping the CMB, looking for really specific anomalies. They're hunting for non-Gaussianeities, these weird distributions of temperature, or B-mode polarization patterns. These twisting patterns in the ancient light could act as actual scars left over from primordial gravitational waves, maybe giving us the first physical footprint of a previous universe.
Finding those faint cosmic scars requires absolute technological marvels. The scientific community isn't just sitting around at whiteboards. We are deploying highly specialized instruments to scour the heavens. We're building on the incredible legacy of the Planck satellite, which gave us our most detailed map of the CMB to date. Today, tools like the James Webb Space Telescope are pushing our visual horizon further back than ever before. Meanwhile, you've got ground-based observatories like the BICEP Array, situated in the freezing, hyperclear atmosphere down at the South Pole, and they are staring deep into the microwave background specifically to hunt for those elusive primordial gravitational waves. Every new sensor we deploy, every single petabyte of data we process, pushes us one step closer to grounding these wild theoretical models in tangible modern science.
Part 5. An Infinite Reality. Exploring the grandest perspective.
You know, the truth might just be stranger than anything we have ever imagined. From a purely evolutionary standpoint, the human brain is wired to understand reality in very linear terms. We expect a clear beginning, a middle, and an end. So when we try to grapple with concepts like quantum vacuums, eternal inflation, or 11-dimensional space, it feels completely counterintuitive to our biology. The actual mechanics operating behind the curtain of our cosmos are so profound, so entirely foreign to our everyday experience, that they sit right on the absolute edge of human comprehension. Until we isolate that hard evidence in the CMB, the true nature of our origins remains one of the greatest scientific frontiers we have.
So the crucial point is this: we absolutely must embrace the scale of our own ignorance. The reality we experience on a daily basis, the billions of galaxies we can see, the complex physics we've decoded, everything contained within our 13.8 billion-year-old observable sphere, all of it could just be the equivalent of a single atom inside an infinitely larger cosmic structure. It's like a giant puzzle, and we only have one piece. Our entire vast universe might simply be a brief, localized event within an unending, eternal landscape. Pretty humbling to think about, right? I want to leave you with this ultimate, provocative question. Did time even have a beginning, or has there always been an endless, evolving cosmic reality? Pondering this profound unknown is a reminder of something truly extraordinary. It reminds us that exploring this immense mystery isn't the end of our understanding, it's honestly only the very beginning of our journey. Thank you so much for joining me in this explainer, and definitely keep exploring the incredible mysteries of the cosmos.